Hello and welcome to Sparky Help. In this video we will look at sizing, earthing and bonding conductors. We can do it the easy way or we can do it the adiabatic way, but we'll also look at how to size earthen conductors and supplementary bonding conductors and also main ekpotential bonding conductors. So before we do that, we need to look at each of those conductors and remind ourselves what they all are. So let's start with number 3 right in the front there at the very bottom, and that connects to B, and B is the main earthing terminal, and number 3 is your earthing conductor. So the earthing conductor is the one that goes to your source earth, which in a TNCS, which will come from the neutral link, in a TNS, that will come from the sheath of the cable, and a TT, that will go to your local earth electrode. Obviously, if we remove the earthing conductor, you will lose the earth to your building, so never remove this before turning the power off. Size of the earthing conductor will vary, and this will vary based on the incoming size of your supply in most cases, but we will look at what they happen to be. Number 1, the most common one that you will probably see up there, number 1 is your CPCs, the circuit protective conductors, which obviously go with your lights, your sockets, your power, or whatever else it is you're running out, and that is one of the things that we will look at sizing. Number 2, another very common conductor, and those are your main protective bonding conductors, your main ekpotential bonding, which goes to your water, your gas, your structural steel, your lightning protection maybe, or any other type of extraneous conductive part. Another one up there is number 4, which is the dotted line, the supplementary protective bonding conductors, as it's got in brackets, where required. So we'll look at the sizing for those, for if anyone out there that still does it. So why do we earth? The installation earthing arrangements, this is from our regulations, as you can see from 542.1.3, lots of numbers. The earthing arrangements shall be such that, and you've got to meet these 3 requirements. So the value of the impedance for the consumer's earthing terminal to the earth point of the supply for TN systems. Earth fault currents and protective conductor currents which may occur are carried without danger, particularly from thermal, thermomechanical and electromechanical stresses. And number 3 on there, they adequately robust or have additional mechanical protection appropriate to the assessed conditions of external influences. So we may need to put additional protection around them if the earths or CPCs or the green and yellow cables aren't necessarily big enough. So that's what we're required to do. Protective conductors, how do we size them? Well, there are 2 ways that our regulations actually refer to, and it says the cross-sectional area of every protective conductor other than a protective bonding conductor. Okay, so not that. This is your CPCs pretty much we're talking about, and maybe the earthing conductor as well, because it's all part of the same thing. Shall be, number 1, calculated in accordance with Regulation 543.1.3 or selected in accordance with Regulation 543.1.4. So it suggests that your protective conductors have got to meet one of those 2 requirements. So let's look at 543.1.3. The cross-sectional area, where calculated, shall not be less than the value determined by the following formula. This is the Adiabatic Formula, which gives reference to another British standard. So S is equal to the square root of I squared times T divided by K. Underneath it says this equation is adiabatic equation is applied for disconnection times not exceeding 5 seconds. Underneath, also below that, it tells you what all those S, I, T and K all mean. And it's a long-winded calculation, but one I will cover. Where it is desired not to calculate, and I think that's most of us would prefer not to calculate if required, the minimum cross-sectional area of the protective conductor in accordance with 543.1.3, the cross-sectional area may be determined in accordance with Table 54.7. Where the application of Table 54.7 produces a non-standard size, a conductor having a larger cross-sectional area shall be used. And I would say probably most electricians out there would know how to size an earth, and they probably won't need to look this table up, they would probably just know it. Do they remember it comes from Table 54.7? Probably not, but it used to come from Table 54G. So what does this table actually say? Well, it hasn't changed in all the time that I've been looking at it. So table 54.7, minimum cross-sectional area of a protective conductor. So basically, if we look at the first column, first of all, that says cross-sectional area of the line conductor. So it's your earth is sized against the line conductor. Remember, your line conductor will probably be the same size as your neutral conductor. If we look at this, it says S is less than or equal to 16 mil. So what does that basically mean? It means cables from 1 mil up to 16 mil. So if you know your cable sizes, that's 1, 1, 5, 2, 5, 4, 6, 10 and 16 mil. So that's those sizes. The next one down says greater than 16 and up to 35. So there's only 2 cable sizes in that particular size. Why they don't just write it, I don't know, but they don't. So it is 25 and 35 mil as our standard cables. Below that, the very bottom one is any cable size that is bigger than 35 mil. So if we look at the middle column, which is the one which is important, relevant to us in this very easy guide to it, is if you have a 1 mil cable on the left hand side of your line conductor, then the second column along says, right, in that case then your CPC must be the same size. In fact, you keep the CPC the same size as the line conductor up to 16 mil. If you do this, you do not need to calculate, it will work. Going on down, the next one down, remember it's greater than 16 and up to 35 mil, so that's 25 mil and 35 mil cables. It's saying that the CPC, the earth protective conductor that you're going to put in, will be 16. So if you think about your tails that you might put into a domestic installation, 100 amp supply, the meter tails are 25 mil. The earthing conductor that you would put in would be 16, and this is what the electricity company would quote you for 100 amp. But if it was a 35 mil, then it would be 16 as well. That's also required. The very bottom one is basically saying cables bigger than 35 mil, and the largest one they make in a copper cable is 1000 mil, and it's basically saying you divide that cable by 2. So if you had a 50 mil cable, you divide that by 2, that becomes 25, and they make a 25, so a 25 mil earth is what would be required. However, if you was to put a 95 mil cable in, half of 95 is not a round number, so you don't do a half size of 95, but the next size up would be a 50. So a 50 mil is what would go in. So the best way to have a look at this is actually just have a look at some questions that I've just put together. And I've just put some questions here. So we've got line conductors and different sizes. But then I just swap it around a bit. For F, I've just said, right, okay, this was your CPC. So what size line would you get for each of these? So if we look at the first one then, because it's a 6 mil, it means the earth that you would put in would also be a 6 mil. And this is all size to table 54.7, a bit like a rule of thumb, really. And then 16 mil, well, hopefully you've looked at that, and that would also be a 16 mil. 4 mil, if your line conductor is a 4 mil, remember your neutrals will probably also be the same size. There would also be a 4. For a 70, well, that becomes a 35. For a 150, well, half of 150 is 75, but they don't make a 75, but the next cable up is a 95. So 95 mil would be the size of your earth that would go in for that. I've just turned it on its head. It don't normally work this way, but just to see where you'll go with it. If you had a 10 mil CPC going backwards, therefore the line conductor would also be a 10. If you had a 25 mil, it would be double that size, so it becomes a 50. So you would have a 50 to go with that earth. If you had a 150 earth, then double that. They do make a 300 mil. And a 95, well, that's similar to the one above, so you would end up with a 150. So that's a very quick, easy way. And if we do this and we size our earths according to table 54.7 of BS 7671, you will always get it right. It may not be the smallest you could have got away with, but it will work. But what about twin and earths, I hear you say? Twin and earths have a different size CPC built into the cables. I guess then everybody out there is actually doing the adiabatic equation, because this doesn't follow table 54.7. So if we have a 1.5 mil squared twin and earth cable, the CPC typically is around 1 mil. So therefore everybody must be doing the adiabatic equation. But we don't. In the on-site guide it tells us that if you multiply your line conductor resistance by 1.67, because that's the ratio difference in conductor size, that would give you the resistance of R2 to give you the CPC resistance, which would then allow you to go off and work out the resistance and work out the adiabatic. However, we don't need to do that either, because there's a guide within the on-site guide, and it's one of these pages here. This is a particular page, and there are many pages like this that cover most standard types of circuits. And if we look at this, we have got multiple columns, and in the first column it gives you a typical, for lighting circuits, it gives you typical circuit breaker sizes. So if in a domestic installation you would probably put a 6 amp, and we would probably go for a type B. Then the third column over gives you conductor sizes. So are we putting in a 1 mil, or are we putting in a 1.5, or whatever it happens to be. So let's go for 6 amp type B and a 1.5 with a 1 mil earth, and we can see that on there. And if we look across, the fourth column over gives us installation methods. So 101, 102, 3, A and C. So this is clip direct, this is on the side of a joist, it's touching plasterboard. So providing you're installing it in that way, then we can look straight across to the other columns, and at the very top you can see the type of earthing system. So if it is a TNS or a TNCS, and it with or without an RCD, we can look across there. So if we look at up here at a TNS at 0.8, and this is a maximum of 0.8, that's what you've got with an RCD, 30 milliamp. Moving on down, that will have 106 meters, and this is the maximum length of run for this cable. And if you install 106 meters or less, and providing the load is distributed evenly for this particular cable, you will meet all requirements. It only comes into a bit of a problem if you start looking across here, if you go to a type C breaker, and then if with no RCD the maximum length of run now is 78 meters. You'll notice it says ZS after it, because basically what that means is the maximum ZS for this protected device would fail if you went longer than 78 meters. In other words, the ohmic value, the resistance, is too high. You'll notice some down on the bottom, on the 10 amp at the very bottom of the page down here, they say VD, and that means they would fail on volt drop. So you'd have to make sure you stayed less than 42 meters if you were looking at this one here and installing 1 mil on a 10 amp. Okay, so you would have to keep the lengths of run quite small. I say quite small, 42 meters is quite a long way to go, but it's a very quick way. So if anyone ever asked, did you work out using the adiabatic equation? Your answer is no, of course I didn't, because I looked in the on-site guide and this gave me my lengths of run, and I've installed it as per these tables. So, quick question for you. True or false, steel conduit can be used as a circuit protective conductor? It's all true. The following can be used as circuit protective conductors. So this is from our regulations, and the following can be used. So a single core cable, we knew that. A conductor in a cable, of course it could. A bare conductor in a common enclosure with insulated live parts, well, that definitely can be. A fixed bare or insulated conductor, that can be. A metal covering the sheath, screen or armouring of a cable, definitely. Metal conduit is in there, including trunking and all the likes, because they are actually very good conductors. And also at the very end there's an extraneous conductive part, but it's got to comply with that, which can also be used as protective conductors. But what if the earth gets buried, such as to an earth electrode, as in this example here? So the moment the cable gets buried, because to an earth electrode that's probably a high resistance in overall scheme of things, and that would limit the fault current. So it isn't necessarily you're going to put cables in to carry an amount of current that's going to flow, because there's probably not a lot in comparison to other earthing systems, because this is typically TT. But it's about the fact that you've buried the cable. that is the problem. So we have a set of regulations that if you bury earthen conductors, and this here then says that if it is buried and it is not protected against mechanical damage, but it is protected against corrosion, in other words it's got a green and yellow sleeving around the outside, a sheath on it, then you can get away with a 16mm copper. So the moment you bury it, then it has to be 16mm. However, if you look across, if it is protected against corrosion and you put it in conduit and trunking or something, the minimum in theory you could get away with is a 2.5mm squared copper cable. Okay, but obviously you would check to make sure it is correct, but these are the minimum cross-sectional areas. Very importantly though is this one here, the very bottom one, because there are many that you see in this picture here where you see earth electrodes that look like this. They're a trip hazard. They're not the best in the world. They probably do the job, probably, but they don't actually meet the regulations. And it says the connection of an earthen conductor to an earth electrode or other means of earthing shall be soundly made and be electrically and mechanically satisfactory and labelled in accordance with regulation 514.13.1 number 1. It shall be suitably protected against corrosion. So how many faults are there with that particular one, and how many times have we come across earth electrodes that look like this? So bonding conductors. So we are talking about main protected bonding conductors within a building. So except where PME conditions, protective multiple earthing, which basically means TNCS. A main protected bonding conductor shall have a cross-sectional area not less than half the cross-sectional area required for the earthing conductor. So bonding, except where PME conditions apply, is based on the size of the earthing conductor, so not less than half of the installation and not less than 6mm. So the minimum size you can get away with is a 6mm within a building, providing it's not PME. The cross-section area need not exceed 25mm. Okay, so 6mm to 25mm is the maximum that you would like to see. However, I will add a caveat on that, and that is the fact that it is on length of run. If your length of run is too high, that may well push your cross-sectional area up because of resistance. However, if you do have a PME installation, then there is a different table for you to look at to make sure you get the right size earthing and bonding in place. So it is very important that we do look at that. For this one then, bonding conductors, minimum cross-sectional area of the main protected bonding conductor in relation to the pen conductor. That's protective earth and neutral, that's the outer sheath, that's the braided bit around the outside of the supply authority's cable. And what that basically says is if it's 35mm or less as their equivalent size, then the protective bonding conductors would be 10mm, and that's fairly standard for most domestic installations in the UK. So 10mm, but obviously as the supply size goes up, it could well be a bigger bonding conductor that you put in, but there is a maximum they state on here, and that is 50mm. But that isn't to say electricity companies may ask for higher, but it's something that you would need to check. So where do these go? Well, I think most people probably know, but just to make sure, they go to extraneous conductive parts. Extraneous conductive parts are parts of metalwork not part of the electrical system that go to ground and therefore earth themselves. That's the important part. They go to ground and they introduce an earth potential. Gas, water and other metallic pipework or anything else. And what it's basically saying is we should bond them as practical as near to the point of entry into that premises. And it says where there is a meter, isolation, point or union, the connection shall be made on the consumer's hard metal pipework and before any branch pipework. Where practicable, the connection shall be made within 600mm of the meter outlet or the point of entry to the building if the meter is external. Here's a little picture that just shows all that and the different locations that you can take them to. So there's the gas meter, there's a water pipe, which we will come back to, and showing where the connections are. So they're on your side of the stopcock, they're on your side on the meter before branch pipework. And if you have structural steel, then it's just a suitable location that you're going to take them to. protective equipotential bonding, and it says in each installation, main protective bonding conductors complying with Chapter 54 shall, and that's the sizing of conductors, shall connect to the main earthing terminal. Extraneous conductive parts including the following. So this is what they list, and it says water pipes, gas pipes, other installation pipework, ducting, central heating, air conditioning, exposed metallic structural parts of the building. But they've got to go to ground. There is a point to remember, and I said I'd come back to it, and this is it. And they've added this in as an addition to this 18th edition, which most people are aware of now, and that is metallic pipes entering the building having an insulating section at their point of entry need not be connected to protective equipotential bonding, because they do not introduce an earth. Therefore, they're not extraneous conductive parts. If you can guarantee that no other metalwork beyond this point that we're looking at now actually goes into the ground, because if any of it goes into the floor screed, so the copper pipe goes into the floor screed, and I know it would probably be covered with material to stop it being damaged, but if you're not sure and it goes into contact with the ground, then you would need to put a bonding clamp on it. So you still might see people just do it because it's just easier to do it rather than trace out for the rest of the building to see whether it does actually go to ground. Has this really changed in the regulations? No, they've just added this note just to make it clearer that actually you don't need to do it, because there are many properties out there that have got plastic incoming pipes and still have bonding to it. I've even heard people say they bond plastic pipes. So there's one other one we've not looked at, and that is number 4, which is the dotted line. The controversial, do we do it, do we have to do it, or do we not have to do it, supplementary bonding conductors. So there we've got between M and M. Okay, and if we're not sure what M and M are, we've got exposed conductive parts. That's what M is. And C, we've got there's an extraneous conductive part. So M is exposed conductive parts. That's a piece of electrical equipment which has a metal case or earthing to it. And C is extraneous, so that could be water pipe, structural steel, or something like that. And it's the sizing of conductors and the regulations that go with this. So here are the set of regulations that apply to supplementary bonding, and there are 5 of them really. But probably the most common that people are aware of, and that is that you can get away with having just 2.5 between exposed conductive parts, providing it is with mechanical protection. Without mechanical protection, then it has to be, you can get away with a 4mm. However, in some cases it does depend on what conductors are connected to it. So if you have live conductors going into something, then the bonding is based on the size of those conductors as well. So let's look at number 1. It says a supplementary bonding conductor connecting 2 exposed conductive parts shall have a conductance, if sheathed or otherwise, provided with mechanical protection, not less than that of the smallest protective conductor connected to the exposed conductive parts. If mechanical protection is not provided, its cross-sectional area shall not be less than 4mm. So it's not less than half of the smallest protective conductor of the 2 circuits, or the circuit that you've got there. But if you don't provide mechanical protection, then it goes to minimum of 4mm either way. The next one down says supplementary bonding conductor connecting an exposed conductive part to an extraneous conductive part shall have a conductance, if sheathed or otherwise, provided with mechanical protection, not less than half of that of the protective conductor connected to the exposed conductive part. If mechanical protection is not provided, its cross-sectional area should not be less than 4mm. So this is talking about going from an exposed to an extraneous, that's a structural steel or a pipe or something like that. And if you've got conductors going in it, so it's got to be not less than half of the protective conductor of the circuit. If you do provide mechanical protection, then you can do that. If it's not got mechanical protection, then it becomes a 4mm. Next one down, a supplementary bonding conductor connecting 2 extraneous conductive parts shall have a cross-sectional area not less than 2.5, if sheathed or otherwise, provided with mechanical protection, or 4mm if mechanical protection is not provided. So that's a fairly common one. So supplementary bonding between 2 extraneous conductive parts, so that might be between your flow and return, or your hot and your cold, whatever it happens to be. And typically most people would probably put a 4mm in. However, I have heard people say they put 6mm in. Probably why they put 6mm in, it's probably because 6mm is what they have and they don't have 4mm with them. but it's perfectly acceptable, but as long as it's bigger than 4mm or 4mm or larger. But obviously if you're going to bother to put conduit in between the pipes, then you could get away with putting 2.5, but if you've got time to put conduit in between the pipes, well done you. So let's just have a quick look, because that's the best thing to do, at an example. And we've got here then, between the two exposed conductive parts, we've got number 4, which is the dotted line, which is a supplementary bonding conductor, but we'd need more information. So if what we're saying is it is a 1,5 and a 1,5, well, if we look back at the previous regulations, you can actually skip back, have a quick look, or open your book and have a look yourself. And hopefully what you might find is that you could get away with a 1,5 with mechanical protection, or a 4mm without mechanical protection. Now if we look, then it is a 4mm and a 4mm. Well, hopefully that's made things a little bit clearer for calculating and sizing earthing conductors and all the different types of earthing that I use. So please like and share the video, and I'll see you again soon. Thank you.